Electrostatics, Day 130. Electrostatics is the study of electric charges at rest. You can see the two root words there are electric, and static means not moving, at rest. And there are two basic electric charges, the electrons, which are negative, and the protons, which are positive. There are some subatomic particles that we will study later, quarks and leptons and so forth, that may have partial charges of these, but these are essentially the fundamental charges. And as you learned in chemistry, the electron and proton are the same in magnitude, so they can cancel each other out and neutralize. That's basically the whole basis of chemistry. But what you didn't talk about in chemistry were the units that go along with charge. The units for charge are coulombs, or the Coulomb, C-O-U-L-O-M-B, symbolized with a capital C. The electron is negative 1.60 times 10 to the negative 19th coulombs, and the proton is positive 1.60 times 10 to the negative 19th coulombs. The unit was defined before we really knew the size of the charge in the electrons or protons. Otherwise, they might have used a smaller unit as the fundamental unit for these concepts. As you may recall, the fundamental rule of electrostatics is that like charges repel, opposites attract. In other words, two electrons will repel each other, two protons will repel each other, but a proton and electron will attract each other. So some questions that follow are, what keeps electrons in orbit? Well, this is the rule that does keep electrons in orbit. They're attracted by the protons, the fundamental rule. The protons attract them. But what keeps the nucleus together? Because we know in the nucleus there are neutrons and protons. The protons are repelling, and they're in close proximity to one another, so why doesn't the nucleus blow apart? Well, it turns out that there's another force involved. It's called the strong nuclear force. That supersedes or is stronger than the repulsive force of electrostatics. Turns out in nature it's commonly understood now that there are four basic forces in nature, and everything can be grouped into one of these four categories. There's gravity, which is one of the fundamental forces. The electrostatics force, electric force, is the second fundamental force of nature. The strong nuclear force and the weak nuclear force. So these are the four fundamental forces. We'll be mostly talking about now for the next few weeks the electric force. The law of conservation of electric charge, which is a lot like any other conservation law we've had so far. Electric charge cannot be created or destroyed, only moved around. What you may have done in your past, or you'll see me do in class, let's say I have a rubber balloon. I blow up a rubber balloon, and I rub it in my hair. Well, it turns out that a lot of times there's some loose electrons in fuzzy objects like hair and sweaters and carpeting and so forth. Let's say, for example, if I have a balloon that's neutral, it's got equal amount of electrons and protons, and my hair is neutral, equal amount of electrons and protons. And I take a balloon and I rub it in my hair. What happens a lot of times is there's some loose electrons in my hair, and when I rub a balloon in my hair, it will pick up some of those electrons out of my hair, and the balloon will become negative, and then it will stick to a wall or to another object. What happens is if there's 20 electrons, it's probably more than that, but let's say there's 20 electrons that transfer out of my hair, the balloon becomes charged with 20 times the negative 1.60, so a net negative charge of 20 times the basic charge of the electron. But my hair then would be positively charged if it's now missing some electrons. It would be just the opposite of the balloon. Because I cannot just create a positive or negative charge from nothing. I'm just moving electrons or protons around. Normally it's the electrons because they're more easily accessible since they're orbiting around the outside of the nucleus. It's very hard to deal with protons, or to extract a proton from the nucleus requires a nuclear activity or nuclear process, which is not easily done. So anyways, charge can only be moved around. Forces that work at a distance. Basically all four fundamental forces work at a distance. In other words, you don't need to be touching to have this force be active. For example, in Newton's law of universal gravity, just a quick review here, the force of gravity, F sub g, from last semester is capital G times mass sub 1, mass number 1, times mass number 2, divided by r squared, the distance between their centers, squared. So that was a fundamental rule or law that Newton discovered. It's active between any two masses in the universe, any two planets and suns, but even between two people or a person in a chair, except for in that case the force is so small because the masses are so small. But it's a fundamental force of attraction between any two objects of mass in the universe. Now, Coulomb's law, which is basically the electrostatic version of the gravity law right there, F sub E, the force of electricity, static electricity, is equal to K times Q sub 1 times Q sub 2 divided by R squared. That right there is very, very similar to the gravitational force. It's the same in structure. It doesn't take a rocket surgeon to see, to hear that that's the same equation, just different letters, basically. It's the same format. So there's an interesting structure to the universe, which I think is designed in by God, that shows the same types of relationships. Here we have K instead of G for the electric force. K is what's called Coulomb's constant. It will be given to you as 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q now is a new symbol. It is the symbol for charge. The units for charge are capital C, so we got to keep that straight. Q is the sign for, or the symbol for charge. C is the unit for charge, coulombs. So it's K times Q, the product of the two charges. So it could be the charge of a proton times the charge of a neutron, or electron, not neutrons, they have no charge, divided by their distance squared. And once again, the distance should be from center to center, but that's a little bit easier to imagine in this case because these charges are so small. They're basically pinpoints anyway, so the idea of from center to center is very easy to conceptualize here. Here's an example. You have two charges. You have a 2 Coulomb and a 3 Coulomb charge. 2 coulombs and 3 coulombs. All right, so what is their force? What's the force here? In this case, I can show you with the diagram that since they're both positive, that means they're both like charges. When we say like or opposites, when we say they're like charges, not because they're the same charge, they're different magnitudes, but they're both positive. If there's no sign in front of them, we assume they're positive. Well, what that means is that these two charges will repel each other. That's how we can show that. I'm just going to plug into that equation up there the values. The force of repulsion here, the electrical force of repulsion, will be K, which is 9 times 10 to the 9th, times the 2 times the 3, divided by their separation distance. Be careful with the units there. It's meters. You want meters. So that's 0.47 meters squared. In this case, if you plug it into your calculator, you end up with the electrical force of repulsion here is 2.44 times 10 to the 11th newtons of repulsion or repelling. Remember, it's a vector. There's a size and a direction here. The direction is not so important when you only have a pair. As you'll see in the next examples, when you have 3 or 4 charges involved, the directions become more and more important, and then you have to get into vector and vector addition and vector components. But here's two charges that repel each other with a very, very large force, because this is somewhat of an unrealistic situation. A 2 Coulomb and a 3 Coulomb charge are actually very, very large charges. Usually we'll be dealing with micro and nano charges. But here, since we have a 2 Coulomb and a 3 Coulomb charge, which are basically about a half meter apart, the force is immense here. 2.44 times 10 to the 11th newtons is a huge, huge repelling force because these are really large charges. So that's Coulomb's law. It's the force of either attraction or repulsion between any two charged particles relative to each other and how far apart they are.